more video to talk about here is Hopital's rule. So once again, here's the statement of Hopital's rule. So note that what we have here is we have limits as x goes to some fixed finite value a here. So we might wonder what happens if x goes off to infinity. And so as it turns out, we do have a version of Hopital's rule for limits as at infinity. So what's going on here is that, I mean, you can read everything through, but if we have the limit as x goes to infinity of f of x, and the limit as x goes to infinity g of x, both exist, and either we have 0 over 0 or infinity over infinity in determinate form, then yes, we can do the limit as x goes to infinity of f of x over g of x is equal to the limit of x goes to infinity of f prime of x over g prime of x, again, provided that the limit on the right exists here. I wrote this up for limits as x goes to infinity. You could also have this as x goes to minus infinity. Same kind of thing would work here. And so why would we care about this? So oftentimes we wonder about what happens if we have a couple different functions. We might wonder, like, which one grows faster in the long run? And so we might have here notation g of x double less than equal to f of x. We would say here g of x grows more slowly in the long run. And more formally, what is this? We would have this be here, that the limit as x goes to infinity of f of x over g of x is equal to infinity, or the limit as x goes to infinity of g of x over f of x is equal to 0. So if the ratio of f of x to g of x in the long run as x goes off to infinity is infinity, then g of x grows more slowly, f of x grows more quickly. So why might we care about this? Well, one great application of this is to the runtime of computer algorithms. So for example, if we have, we might have two sorting algorithms, if you're into computer science, quicksort and bubble sort. And so the thing that we would learn is that quicksort, you have to know what quicksort is if you're in computer science classes. You'll learn about it at some point. Quicksort is what we would say the runtime is n natural log n. Bubble sort is an n squared algorithm. If we want to convert this to x notation, we could say here g of x is equal to x natural log of x, and bubble sort f of x is equal to x squared. So what I mean by this notation is that plug in how many, let's say we want to bubble sort a list of 1,000 objects. It would take, on average, according to this, on average 1,000 squared operations, 1,000 squared steps. If we want to plug in, use quicksort, it would take 1,000 times natural log of 1,000 steps. That's the kind of thing that we would be thinking about here. And these are approximations. We'll take them as exact to make our calculations simpler. These are approximations. So we might wonder which one grows more quickly, more slowly in the long run, because 1,000, that's not a lot of things for a computer to do. Computers, we want them to be able to handle cases with 1 million or 1 billion pieces of input. So really what all of this is asking for us to do, this is asking for us to compute what's the limit of x squared over x natural log of x. So we see that we can cancel out, oops, I forgot, limit as x goes to infinity. We can cancel out a factor of x here, but we're still left with limit as x goes to infinity of x over natural log x. And at this stage, both x and natural log x, as x is going off to infinity, so we're in infinity over infinity indeterminate form. And so we can use Hopital's rule here. So let's say here we're using L'Hopital's rule. The derivative of x is 1. The derivative of natural log x is 1 over x. And so that swings upstairs. Limit as x goes to infinity of x. And so we just have infinity. So the overall limit here of x squared over x log x that x goes to infinity is infinity. And so we do conclude that x natural log x grows more slowly than x squared. One more important application of this has to do with e to the x. So here is a fact. Here is a fact that x to the n grows more slowly than e to the x for all n. In other words, that's the same thing as saying the limit as x goes to infinity of e to the x over x to the n is always equal to infinity. And we can see that. We can see that by, we're just going to do it for positive values of integers here. And it's just going to be many, many, many applications of L'Hopital's rule. So we do e to the x over x to the n. So this is as x goes to infinity. We have an infinity or infinity indeterminate form. So by L'Hopital's rule, the derivative e to the x is e to the x. The derivative x to the n is n times x to the n minus 1. We still have infinity over infinity. And so the derivative e to the x is e to the x. The derivative of n times x to n minus 1 is n times n minus 1, x to the n minus 2. We apply L'Hopital's rule again. E to the x over n times n minus 1 times n minus 2 times x to the n minus 3. And so the thing that you should realize here is that the numerator is always staying as e to the x, and the denominator is losing a power of x each time. It's going from x to the n to x to the n minus 1 to x to the n minus 2 to x to the n minus 3. We're losing a power of x each time. So eventually, x to the 10 becomes x to the 9, becomes x to the 8, becomes x to the 7, 6, 5, 4, 3, 2, 1, 0. Eventually, we end up with a limit as x goes to infinity of e to the x over n factorial, and that's a constant. And that's how we would end up concluding that the overall limit here is infinity. So e to the x beats any, it grows quicker, it grows faster than x to the n for any exponent n. Okay, so let me end this video. I actually should have put this pre-class problem at the end of the previous video. My apologies, but here's our final pre-class problem. So you want to do this similar to in the previous video. Take natural logs to be able to evaluate the limit as x goes to infinity of x to the 1 over 2x.